I want to talk about Ethernet APL and why we believe OPC UA FX entry into process automation will be actually Ethernet APL. My name is Volker Goller, Analog Devices. I'm a technologist in industrial connectivity and controls, and let's get started. So again, what is Ethernet APL? Okay, so first of all, it is Ethernet. It is a standard Ethernet physical layer with some extra properties. It is a 10 megabit intrinsically safe Ethernet, and it's based on IEEE 802.3 CG 2019, or better known as 10BASE-T1L. It is long range, up to 200 meter with intrinsic safety, 1000 meter without intrinsic safety. It's a single twisted pair cable transport for both data and power. The interface is polarity agnostic, which is really great for the process guys. You put the wires this way in, it works. You put them that way in, it still works, no difference. And it can provide power into intrinsic safe zones, and that is 15 volts and 0.54 or 1.1 watt, depending on the intrinsic safety zone. And we will get to some of the details in a moment. But in the great scheme of the layers of the internet communication, it's down here, a physical layer just like any other. So many of you have never been really close to process automation and intrinsic safety. What is that? We all know functional safety or things like that. But what is intrinsic safety? Well, device is operated in an ignitable environment. That's really the key here. Any spark may cause a very expensive and maybe even life-threatening event. So really translates to do not create any spark or ignition. So some of the device parameters that you have to cover for this, the power needs to be well below 2 watt per device. And that includes the stored energy. You know, if you have a device, you power it up, there are capacitors and inductors, they store energy, and even if you pull the plug, there's still energy in the device. So the overall power envelope includes this stored energy, because stored energy can also do harm. So there is a certain need for current limitation. It needs to be fail-safe device design, and it has actually the limitation in the voltage. You can't go in with 24 volts or something. You have to be take care. And yeah, I mean, these explosions are real. There are big incidences in gas and oil and chemical that have been caused by sparks, not by measurement devices, but maybe by reconstruction. Somebody uses a grinder where he shouldn't, and really bad things happen. Okay. So before we really understand the full beauty of APL and what it brings to the table, we need to do a bit of history. And the history is a 4 to 20 milliamp interface. So this interface is around for more than 40 years, I guess. It is very successful. It's everywhere, but it got some limitations. And let me tell you this. So let's go to the right, the physical sensor. You may have, let's say, and I use temperature sensing here as an example, but all the other sensing technologies and process are pretty much similar. So you have a sensor, let's say PT100 or something. You have the physical sensor. Then you have to have close to it the so-called temperature transmitter or measurement transmitter, which basically knows how to read the temperature from that sensor. And that is now used to create an analog current on the connection. Wide current. Current is very robust. You can easily control it, and you can make sure that current is not disturbed that much. So it is robust. Again, sorry. The beauty of the current interface is you have 4 to 20 milliamp, not 0 to 20 milliamp. The 4 milliamp is a current that is always on the line, and that means you have about 60 milliwatt going over the line, even on idle. And from this 60 milliwatt, you can usually 35, 37 milliwatt harvest to actually power your temperature transmitter. And on the other side, if there is a line break, you have 0 current, and that is a fault detection. So it serves two purposes here. And people love it because of 4 to 20 milliamp interface. You can debug with a multimeter. You measure the voltage, you measure the current, you know what's going on. On the equipment side, the 4 to 20 milliamp is then usually connected to remote I/O, where you read the voltage drop over a measurement burden, and then you have a formula to take the measured voltage that represents a current, that represents a temperature, back to real value that is actually a temperature. And what is obvious here is that all components, or specifically the more complex components like the remote I/O and the temperature transmitter, needs to be configured. You need to tell them, oh, what type of temperature sensor is out there. And the remote I/O needs to understand with which temperature sensor I'm connected. What does the current mean? Other than that, you're pretty blind in the system, and you don't get what you want. So everything has to be configured and configured separately. That is very tedious, and you need some good people to understand that, and get such a big chemical plant commissioned is not an easy thing. You need trained people. So to improve on that, HART was invented, and HART is really a way to have a modulated signal on top of the current loop to have at least some data exchange between the remote I/O and the temperature transmitter. And what HART is, it is very much like what we had back in the 80s. Yes, I'm that old. My first modem to access the World Wide Web, well, back then it was mailboxes, not the internet yet, had 1,200 baud. That is exactly what HART has. It is very slow, but it has a big advantage in commissioning, because now the remote I/O and the temperature transmitter can communicate and at least make sure, yes, you are the temperature transmitter that I think you are. And to some extent, you can even configure the temperature transmitter through the remote I/O. So yes, now you have a big advantage. And as people of the industry keep telling me, they use HART mostly for commissioning. Once everything is up, it falls back to 4 to 20 milliamp, and HART is rarely used. The interface has a few shortcomings, obviously. If you think about it, if you want to do a combined sensor, let's say pressure and temperature, yeah, now you have a problem. Either you use HART as a second channel, or you pull two pairs of wire, because an analog value like current can only transport one value. So it has its limitations, but it is extremely simple, robust, and people are trained. The problem is only people who are trained are going to retire in the next 5 years. And the younger generation thinks, we don't want to spend a day running around the facility just to understand what is connected with what. And using a multimeter to debug seems to be a bit Stone Age technology. We don't want that. Can't we have Ethernet? And that is exactly what APL brings to the table. We bring Ethernet down to the temperature transmitter or flow meter or level meter or whatever sensor is out there, or even actuators. So now we have an Ethernet connection. It is 10 megabit, so that is slow by our normal Ethernet expectations, but it's actually very fast compared to hard. And we can now build devices that have multiple measurement values. We can do all the things we love with Ethernet. We have things like LLPD, so we know who our neighbor is. We can do automatically a plan which port of our switch is connected to which hockey puck. Sorry for that term, but sometimes the temperature transmitters are just called hockey puck because they're round and small. So yeah, we have all the beauty of Ethernet, all the protocols, everything you have, you love about your Ethernet device is now available on APL or through APL. And the beauty is it is all just software because the intrinsic safety is a physical parameter. It is only hardware design related, it is not software design related. So there is no software component of intrinsic safety that we have to take care about. So it is unmodified Ethernet. And the remote I/O goes away. We have just a switch. Well, it has to be a specific switch because now we do intrinsic safety. It has to support the properties of intrinsic safety connection. But other than that, it is a switch. It's not a gateway. Your controller doesn't talk with a remote I/O, and the remote I/O talk with a temperature transmitter. No. You talk directly to your measurement point and have all the beauty of Ethernet to the edge. So obviously there's a big question in the room, and that is a question that many people get wrong. APL is SPE, or is it? What is the relationship between both? And there is actually a relationship. They both use the same physical standard from Ethernet, the 10-base-T1L. The only difference is really intrinsic safety and the different power schemes, power providing schemes that comes with it. So with APL, we learned it's 15 volts. It has limited power. It goes a long way with physical protection devices to make sure we can go into this ignitable atmosphere. But SPE doesn't have that problem. So for SPE, we have a different power scheme where we can provide actually 24 volts, 55 volts. And we have 6 different power classes that are auto-net across the links. And we can go up to 52 watts, which is quite a bit. So some actuators may be fully driven by that or certified by that. So that is really the difference. So APL, limited, intrinsic safe, SPE, not limited or lesser limited to the power. APL, engineered power, you turn it on, you know this port needs to be driven, you turn on the power, everything is good. And there is no big problem with that because you only provide a bit of power. If you provide more power, you need to negotiate upfront to figure out if you have the power to drive the device and all that. So these are the two things. The main differences between APL and SPE. Anyway, Ethernet is both. So if you have a software solution that runs APL, it probably runs exactly on SPE. Maybe you use a different device model. Maybe you use extra protocol features for APL because of the broader process automation requirement. But it is Ethernet. From the protocol, it's all the same. And there is the 100-base-T1L at the horizon, a 100 megabit version of the 10-base-T1L, which gives us more power. This is specifically interesting for SPE, and it fulfills latency requirements for daisy-chained devices, even at least up to 200 meters. If you go 500 meters, you want to activate forward error correction. So you get a bigger delay. And in the latest edition of the IEC 634444, which has been completed just before the Hanover show this year, a joint working group of OPC Foundation, ODVA, Fieldcom, and Profinet has been completed. It is in review now, and it's covering now both APL and SPE for 10 and 100 megabit with all the information you need, how to calculate cable lengths and power classes, and all the information is in here. So we have a common standard for industrial communication, how to do powered links based on this technology. Now, after all the history and all what APL is, does OPC UA FX go to play here? And the answer is obviously yes, because in OPC UA we can, or as a guy, I think he's president of the OPC Foundation, used to say, OPC UA is a data model. And we can model all aspects of an APL or SPE device in OPC UA, inputs, outputs, flow meter, temperature. No matter what you do, it is possible to model it with OPC UA. So along with the required location data, asset management information, whatever we need in a device, we can model it in OPC UA, and that is a big plus. And an APL device can connect to the control room as well, to other tools, say asset management tools, so we're more flexible here, or the cloud or whatever. And it's all secure and in line with the Cyber Resilience Act, which certainly comes down the pipe and will be important for the entire industry. Now I have to introduce you to another concept from the process industry, which is the Namur open architecture. So first of all, who's Namur? Yes, it's a city in Belgium, but also it is a user association of automation technology and process industries. And this organization is a leading organization in defining all kinds of specifications and requirements for the process industry. And NOAA defines a secure device model where the vertical communication is decoupled from the real-time communication. So basically, a device connects to DCS or PLC using a real-time protocol like Profinet or Ethernet IP. And then there's vertical communication, and that can be OPC UA. And to decouple it, there is the so-called data diode. You know, these guys are mostly hardware guys, so they think in hardware, you put a diode in, it can only flow one way. We would call it a read-only access for the vertical channel. And we have seen customers who actually said, okay, but for the commissioning phase, we allow read-write so that we can set up everything through OPC UA, and then when it goes operational, then the data diode goes in place, and then we have only read access from our data models. And the vertical communication allows multiple applications such as control room, asset management, monitoring, alarm handling, and access to the device directly. So how does that look today? Solutions that are out on the market are a bit here on the left side, where cloud control room and all that is attached through an OPC UA gateway that may actually be inside the DCS or externally. And that OPC UA gateway would use a domain protocol to fetch all the data from the field and present it upwards. There is a tendency to do NOAA integrated, which means an OPC UA instance runs on all the devices, field switches on the APL devices, even on the switches, and so all the devices have a direct connection to all these applications and the control room. Both approaches have advantages and disadvantages, but that is what we see today in the field, where people are either moving to or what is actually already operating. And now, with all that in mind, you can make a very short step forward and think, once we have OPC UA FX finalized and we have all the necessary functionality, we can do everything with OPC UA FX. We can run OPC UA FX for the real-time aspect, which pops up, probably TSN between the switches and the high bandwidth network to make sure the traffic flows there protected. We have an uplink to the control room, to the cloud, asset management, whatever you want to connect, can still connect to a client server instance in these devices. And you have one solution, one protocol that serves it all. Some say, well, FX maybe have a big device footprint, but I'm not buying that, because eventually, if FX becomes real in this industry, the domain protocols will no longer coexist. You will just run OPC UA. You may even drop the web server because you don't need it anymore. So you drop a lot of software. Yes, you have to gain a bit, but probably it's just a wash. But we will have to prove that going forward. It is an interesting time to look at this. I believe that could be the future of a process industry. It probably needs a few years, not next year, but maybe the year after that, or the year after that. We'll see. It's probably not 10 years. And if we look on the broader picture on future topologies, we can see that the future of APL and General SPE is actually one that is Ethernet all over the place. It's all Ethernet down to the sensor, down to the edge of the physical world, and it covers everything. Down to the edge, we have powered links where we deliver power and data, but we will also be able to have our classical hop-to-hop devices for high-performance motion. Probably not power here. Power forwarding from port to port is probably a bit more too complicated. It is cheaper to just provide power in these cases. But here on the edge, power makes a lot of sense, and APL is a big success. And given the slow development speed in process industry, this was really quick. And the adoption is really ramping up. So we believe APL will be very successful, specifically because the newer generation of engineers on site need more data and don't have the time for lengthy commissioning of a system. And just here, APL will absolutely shine. And the same technology, because as I said, it is Ethernet. The difference between APL and SPE at that point is only the way power is provided. The same we enable here, we can enable in the factory automation, in mobility, in all other markets, and have sensors connected to the ground scheme of Ethernet. We have everything in Ethernet. With our protocols, we can cover that, can integrate it. It is one secure domain, so no gateways to different ways how security is handled. It's a pretty slick, beautiful outlook. I have modified the picture that I found on the OPC UA website, and I actually added here and here OPC UA FX arrows, because I think that is possible, and it would greatly expand the capabilities of what we can do with OPC UA, and specifically OPC UA FX. And short word about my company. We were the first to release an TMS T1L file to the market. We are in this since 2015, I guess. So very engaged with the community. We have the products, we have a lot of reference boards. If you want to get something started, just contact ADI or ADI sales representatives, contact me, myself. We have enough boards and can help you get started. Thank you very much. I hope you found this helpful and informative, and thank you very much for listening.